Hello, welcome to this session. In the previous session, we looked at PLL, or we have actually analyzed simple PLL in transient and in frequency domain. So, I will just plot what we have seen so far. We had loop filter, VCO, and this was in the feedback path. Okay. Here, we confined ourselves to the sinusoidal periodic signals as given by sine of omega in t and V out as cosine of omega out t. Okay. At the end of the last session, we said that we can have a frequency multiplication here if we just have a frequency divider which you can implement by having some other block which divides the output frequency. So, I will call this as frequency divider. Okay. So, this is what we had, but still we kept our input and output signals of this frequency divider as sinusoidal. Okay. Now, the thing is that all the periodic signals which you are going to use in your system, they may or may not be sinusoidal signals. As soon as you think about a clock which is used in digital circuits, you think about this this particular clock has like 0 and VDD, it is a full swing signal and it appears to be like a square wave signal. So, when you are having a square wave signal using this mixer based phase error detector, right, it becomes difficult. Okay. So, at the end of the day, what this mixer is doing is it is trying to find the phase error between the input and the output phase. Output of the mixer is proportional to phase error between the input and the output signals. Between the input signals. So, one is your reference signals and other is the feedback signals. Now, when both the signals are not sinusoidal, how will you define the phase error? How you are going to design that particular block? That is something which is which we would like to learn now. So, in our case, now this phase error detector, this particular block which you are seeing in red, this is PD, and we will look at different kinds of phase error detector which will work with sinusoidal signals, with the square wave signals. Okay. Then depending on the signals which we are having in the system, we will choose the phase detector. So, in this session we are going to learn about different kind of phase detectors. Okay. To begin with, let me just first draw the signals which we have been using and what the phase error detector was doing, sinusoidal phase error detector was doing so far. So, if we have a sine wave, assume that it is a sine wave, okay, and then you have another sine wave. Okay. So, this is just an example, the one in blue is V in, the one in red is V out with respect to time. This is what I am plotting. The phase error between these two signals, if it happens that the frequency is going to be same, the phase error is this. If the frequency and the frequency of both the input and the output signal is same, right, both the frequencies are same, the phase error is defined here as the difference between the 0 crossing of these two signals. So, here it is like this. Okay. So, if the frequency of the two signals are same, then this particular phase error phi 1, phi E 1 which is here, and phi E 2, they both should be same. It does not appear to be same here. So, let me just try to show you in a much cleaner waveform. So, in this case what you see here is I will just extend these two sine waves. Okay. This, the difference between the 0 crossing which you see here, right, this particular difference is constant if the two frequencies are same. So, if I call this as phi E1 and this one as phi E2, okay, this difference is constant, and do not worry about the maths of it. If I write for these two signals where just say sine of omega t plus 0, let us say this is V input, and this is phase offset is 0, and this one is here what we are having is sine of omega t, and what you see is the phase is shifted. So, there is some phase offset phi e 1. Okay. So, the difference between the input and the output phase, if you look at it, phi out of t, it is nothing but omega t minus omega t plus, in this case, minus phase error, right. And if the two frequencies are same, as you see that this error will be constant, it will not change with respect to time. If the phase error does not change with respect to time, that has been one of the locking conditions for the PLL. So, if you think about it, if I want to measure the phase error between two signals, right, if somehow I can measure the difference between the 0 crossing of these two signals, I actually get the phase error between the two signals. What we have been doing previously, we were multiplying the two signals where we had V error as equal to sine of phase error. We were not directly getting the phase error, we were getting signal proportional to the phase error. There is nothing wrong with this kind of phase error detection, it is just that there are other ways also to detect the phase error. So, right now we are only considering two sinusoidal signals which have same frequency, and for the same frequency your phase error will be constant. So, if somehow I can detect this, then I will be able to get the phase error. So, that is the phase error detection exploits this. The other case, well, if you do not always have sinusoidal signals, if let us say one signal is sinusoidal and the other signal happens to be a square wave. So, what will you do? So, here I have one of the signals as sine wave, as you see, and let us say the other signal happens to be square wave, just an example. So, it is an square wave. In place of the sine wave, I am just using a square wave, right. So, what I am going to do is I will try to keep the same spacing between the 0 crossings. So, this is one part of the square wave, then you have shifts here, and then you have the other part going up here. Okay. So, these are the two signals. So, here the phase error will be defined as the difference between the 0 crossings of the two signal. This is the phase error. Okay. So, this is the phase error which you would like to detect. So, phi E1, phi E2. If the fundamental period of the square wave, by the way, this is a periodic signal and it can very well be the clock which is generated by the PLL and used in your circuits. So, the period of your square wave or the fundamental period of the square wave or the period of your sine wave, these two periods are same. If that is the case, the phase error which you are seeing here, this phase error is the difference between the zero crossing of the two periodic waveform. So, here the phase error will be defined as whatever the separation you are having between the zero crossing, I will call that as time delta t. So, it is going to be 2 pi times delta t divided by the time period. Okay. So, when you have such kind of waveforms, you define the phase error not like an integer, because just think about it, if you start writing the Fourier series of the square waveform, right, and you have so many signals, but that is not how we define here. What we define here, the phase error is the separation, the time difference between the zero crossing of the two periodic signals. Okay. And we pick up the point as shown here. If these two frequencies are going to be same, then you know that this phi E 1 is going to be equal to phi E 2. Okay. And similarly, how we are going to detect it, that is something which we will see. Similar to this, when you have one as a sine wave and other as a square wave, let us say we both have square waves. Okay. So, in case I have both of these waveforms are square waves. So, let me just remove this blue one, and one of the waveforms which I am going to have, red one is already drawn. So, the blue waveform, square wave, another clock waveform is like this. They both are periodic waveforms. Okay. So, how I am going to define the phase error between these two square waveforms? Same definition. The time difference between the rising edge of the two periodic waveforms. Okay. So, here also phase error will be defined as 2 pi times delta t, which is the separation between the two zero crossings or the rising edge, divided by the time period t. Okay. So, here you see that as time period increases, as your delta t increases, your phase error increases. This is an ideal representation of the phase error between two square waves. How phase error detector is going to detect it and implement this, that is something which we will learn as part of the phase error detectors. Okay. So, one thing which you need to understand from here is that the phase error detector which we have used so far, that works for the sinusoidal signals, but when you have a combination of sinusoidal and square waves or only square waves which are also periodic signals, then the phase error definition which I am using here is the timing error between the zero crossings of two signals. You can say zero crossing, or you can pick up any point at the peak of the signals or so on. Okay. Because these are periodic signals, so whatever you are going to choose, they are that is going to repeat every clock cycle. Okay. Now, you can think about it that this phase error definition is like only the timing error. Why we are only looking at the timing error? Well, PLL is a block which generates a periodic signal whose period is intact, whose period does not change. So, your sine wave can be your reference signal and your square wave can be your output signal, or square wave can be your reference signal, square wave can be your output signal, whatever it is. What we need to do in the PLL block is we need to generate an output clock in such a way that the rising edge or the period of this waveform, output waveform, that does not vary. Ideally, that should not vary at all. Okay. In real PLLs, it will vary, and it will vary by some amount, and you would like to keep that variation in variation limited. Okay. So, that is what we need to do. So, if that is the case, a PLL is a block where you limit the variation in the period of the signal. That means, you are limiting the variation in the movement of this rising edge. Okay. If the rising edge moves, the period changes. So, we are trying to limit the variation in the time period. So, if we detect only the difference between our reference clock, which here let us say input is a reference clock, and your output clock, which is a square wave. Here, if we just maintain, if we just find out what is the difference between this these 0 crossings, right, then we in the loop we can try to limit that, okay, limit the variation. So, that is why we are looking at only the timing information. By the way, you can say, okay, if that is the case, if I am generating periodic signal, well, a periodic signal can be like this also, is not it? So, I am having this for example, I can have a periodic signal like this also, just an example. Okay, if let us say this is the periodic signal, well, it will be difficult to generate such kind of signal using a voltage control oscillator, but if this is a periodic signal, then it is fine, you can use it in as your clock in some cases, but what we are looking here is the difference between the two periodic points or two periodic voltages in the two signals. Okay. So, that is a part of the PLL, this phase error detection implemented by phase error detectors. There are different kinds of phase error detectors. So, first is analog phase error detector. Okay. One of the analog phase error detectors is something which you have seen. We will go through it quickly. Well, I call this as phase error detectors, but I always write as phase detectors, that is a convention here. So, the first one in analog phase error detector is multiplier or mixer based. This is the phase error detector which we have been using for long. Okay. We will just look at more details of this mixer based PD, how you are going to use it. So, in this case we know this is a mixer, it multiplies the two signals. You are going to use this phase error detectors only when you have sinusoidal signals. So, V input and V feedback. This I call output of the phase error detector as VPD. Okay. I am not calling this as phase error right now, this is the output of the phase error detector. So, this is VPD. Given V in, it may be it is like the 1000th time we are going through this right now. V in sine omega t plus phi in 0 and V out as cosine of omega t plus phi out of 0. I have included the initial phase offsets for the input and the output signals. I have deliberately made the frequency of the two signals as same. So, VPD, now I can write it directly because we have seen this many times, 2 omega t plus phi in 0 plus phi out 0 plus sine of phi in 0 minus phi out 0, right. Now, as we know that this VPD can be just written like this as half of sine of 2 omega t plus let us say phi in 0 plus phi out 0, okay, plus sine of phase error. Okay. Now, in PLL we have this phase error detector and this phase error detector has two components. One is depending only on the phase error, other has a very high frequency component also. When you employ this in the phase error detector and you are having a loop filter, right, the even if you do not have the loop filter gain is 1, let us say you just pass it everything, you have one integrator in the form of a VCO. So, high frequency components will anyways be suppressed. Okay. It depends by how much magnitude, but as you start using a first order or second order loop filter, those high frequency components will be suppressed. Okay. So, what we have been doing earlier, we have been saying that the VPD or the output of the phase error detector has mostly on this component only. This is under assumption that the high frequency component is going to be filtered. So, what we define here is average of phase detector output, that is VPD like this. Okay. The average of this phase error detector output is half of sine of phase error, right. Again, this is something which we have seen, things which we need to understand in little more detail. VPD average with respect to phase error is sinusoidal, as you see here. This is minus pi plus pi, the peak point is pi by 2 and the peak point here is minus pi by 2. Okay. In this case, this magnitude is actually equal to half or minus half. Okay. In case we start having any mixer is going to be implemented by some circuit, it will have swing limitation. So, half will actually change to a by 2. Okay. That it will just half is going to change to a or amplitude a at the end. We are not looking at that right now. So, in this case, the important part is that the phase error, first question which you can ask is why we are concerned about V phase error detector average, because that is what that is the quantity which is going to change your control voltage of the VCO, your VCO frequency and the feedback phase. Okay. It may happen that if you are changing your phase error, right, your value will keep on changing, but for a fixed phase error you will have a fixed VPD voltage. So, if you just look at VPD signal as such, this is just for your case VPD signal, right. It is sine of phase error. If remember, if phase error is constant, it is nothing but you can say a very high frequency which is like 2 omega kind of sine wave. Sorry, it is not damping, but it is shifted by sine of the phase error. That is what you are going to have in case of actual VPD. Okay, with respect to phase error. Now, sorry, this is with respect to time. So, our loop actually processes only this part and changes the frequency. So, that is the part which we are plotting, VPD average. Now, you think about it, even when there are a couple of things, that first this phase error detector output is for positive phase error for now, from 0 to pi it is positive, for minus pi to pi it is negative. Okay. And if phase error happens to be greater than pi, then it will become negative, and here if it becomes less than minus pi, it will become positive. Okay. Now, this is a problem in your system. So, why it is a problem in your system? Well, I am having a phase detector. Okay. I will make this now as a block rather than a mixer, phase detector, and you have loop filter, you have VCO. Okay. You give your input and you are looking for output, and now think about it. If you have any positive phase error, right, ideally if you have a positive phase error, then you should increase the control voltage to increase the frequency and recover the phase. But here it actually depends on whether the phase error is greater than pi or it is within 0 to pi, right. So, if I make, if there is a small change, a small phase error here, this phase error is going to be processed not in a linear fashion by the our phase error detector. Okay. So, even if the phase error is greater than pi, you see the loop sign changes completely, which will create a, which will not making the PLL to go towards lock. Okay. So, one thing which you can just an illustration. So, we have used this example here, right. So, in this case, by the way, in this particular case the phase error is lesser than pi. Okay. So, let us say when you measure this phase error here, which is less than pi, what happens? The phase error is positive. This is your input signal, this is your output signal. Phase error is positive. For positive phase error, VPD output V error is also going to be positive, because we know we are in the sine positive waveform. Loop filter control voltage will also be positive. If control voltage is positive, what happens? The VCO frequency increases. Now, what does it mean? If the VCO frequency increases, then let us say this happens pretty fast, then you can say the next sine wave, if the VCO frequency increases, then if it starts happening pretty soon, then in that case your next rising edge should ideally come closer, because I increase the VCO frequency. Okay. If I increase the VCO frequency, then the time period should reduce, right. The time period reduces, but still you detect the phase error here. Because you detect still the phase error, the frequency may increase further, and at some point of time you will find maybe the very next sine wave may happen to come closer to this. The blue and red aligns, that all these things depend on the other components in the PLL, but this is the thing which is going to happen in actual PLL. When it aligns, at that time the phase error is 0, and if the phase error is equal to 0, control voltage will return back to the same value. So, you will have both input and the output sine waves in this case following each other. That is how tracking happens. Okay. Why this is important to understand is because you had a phase error of one sign, you need to change the frequency of the oscillator in that particular direction, and to minimize the phase error. But if the phase error is greater than pi here, the output of the phase error detector is negative, right. So, you will change the frequency of the oscillator in the opposite direction, you will go away from the phase locking, right. So, this is what will happen in the mixer based phase error detector. It may increase the phase error, and then again what will happen when it comes, it may again go to the positive and it will try to recover the phase error. So, these things will happen. What we would like in a linear system is that if my phase error is positive, it should give me a positive output voltage, phase detector should give me positive output. If phase error is negative, it should give me negative output, because when we have a linear output, then the system will behave in a linear time invariant manner. Okay. Otherwise, see, we cannot say that okay, if it becomes a non-linear, it will not lock well. initial locking in the PLL we have seen a lot in nonlinear fashion, but for the when any change happens in the PLL, it will be well behaved if we have a linear gain for the system. So, what we do is we define the linear range of the PLL of the phase detector, and by the way this range is not the linear range, actually this is the monotonous range, okay, where it is changing only in one direction. So, here linear range of this particular PD, which is more or less the monotonous range, you can call, okay, is equal to plus minus pi by 2, right. So, this is something which we want to define here, and if your phase error is within this range, you will see that okay, the change is in the correct direction and your PLL will lock, okay, without going in the opposite direction. Other thing which we have defined, we will just reiterate it here, the gain of this phase detector, which is defined as KPD, and this KPD gain is defined as the derivative of the average output voltage with respect to phase error, and here this is equal to half of cosine of phase error. Okay. Now, this half of cosine of phase error, if I plot it, what you see here is with respect to phase error, the gain KPD is cosine waveform, which is like this. Okay, we know that this is the sine wave. Okay. So, this is minus pi to pi, this is pi by minus pi by 2 and this is pi by 2. This gain is half here and minus half here. Okay. So, within the linear range, which is your minus pi by 2 to pi by 2, what you see is the gain of the phase error detector is not linear. Okay. This is non-linear, which is another problem for the system. Okay. You cannot do any linear analysis, and depending on what phase error you are having, your gain is different. So, the dynamics of the PLL is going to be different. What do I mean by dynamics of the PLL? Well, if your phase error is actually very close to pi by 2, the phase error detector output, right, we have seen here if your phase error detector output is maximum, right, but in that case when you are applying the change is going to be very small, okay, which is like, okay, I am having to begin with, I have a phase error of pi by 2 here. So, with respect to pi by 2, I get V error half and all this frequency change, it comes back, right. It is like in feedback, you apply this feedback, you apply a feedback here, that particular small change, right, because the gain is very small. So, you can think about it, when the PD gain is very small, in that case the feedback will be very slow. So, for this particular block diagram, you can draw the small signal model like this, PD with gain KPD. So, it actually depends on what is the phase error at a given instant of time. So, let me just write this as KVC over S, because this is a small signal diagram. Okay. So, if KPD is very small, then the loop gain is very less and the loop response will be very slow. Okay. So, this is the problem which you see with this kind of phase error detector. It has the linear range is limited between plus minus pi by 2. The gain of the phase error detector is non-linear in the particular case. Okay. Well, we have been using these things. I have shown you also in simulation that the PLL locks, but when we are considering the linear dynamics of the PLL, all these things are important. Okay. Because unless we know what we can apply linear, can we apply the linear gain model or not, we need to know these parts. Okay. Thank you.